Thanks. So I can't see any of you. Usually I see the audience when I'm giving a talk, but I can only see my screen. So if you have questions, please just speak up. I won't see if you raise your hand or anything. Probably most of you know about classical orthogonal polynomials, but I'm going to start by talking about that. One reason is I view it a slightly different way than people usually do. This part, of course, is the same. Classical orthogonal polynomials are a sequence of polynomials indexed by the non-negative integers with the property that the nth polynomial has degree n, and they're orthogonal with respect to some inner product. If you've got that, then you're going to have what people call a recurrence relation, that multiplying a polynomial by x gives you a linear combination of the three neighboring polynomials. So the one indexed higher, the same one, and the one indexed lower. But I'm going to think of that as being an eigenfunction for an operator. So think of this omega sub n as being an operator, discrete operator acting in the variable n. It's a difference operator, so it shifts the n up by 1 and down by 1, and you have coefficients that depend on n. And then x here, you see, looks like an eigenvalue. It's an operator in n with an eigenvalue in x. Again, that's true for any orthogonal polynomials. The next property is what people use to define classical orthogonal polynomials. So the classical orthogonal polynomials are also eigenfunctions for a differential operator in x. So this is a second order difference operator because it goes up and down by 1. This is a second order differential operator. It involves at most the second derivative. And now the operator depends on x. So it acts in the variable x, and it has coefficients that depend on x. But now the eigenvalue would be dependent on n. And so these are, if a sequence of polynomials satisfies all of these, they're classical orthogonal polynomials. They've been studied for a long time. We basically know them all. There would be some kind of Hermite, Laguerre, or Jacobi polynomials if they have all of these things. And because we're interested in studying more, and these have been studied already pretty completely, people are now interested in generalizations. I'm going to be talking about two different kinds of generalizations. The main one, as Louis said, is what's called exceptional orthogonal polynomials. So follow me back up here to the start. So the thing that's different about exceptional orthogonal polynomials is there's no longer a polynomial of every degree. There's a finite number of missing degrees, and yet, at least in the Hilbert sense, those polynomials still span the same space. You can write every polynomial as a linear combination of them, but it might have to be an infinite linear combination. Of course, it can no longer be just a finite combination. And if that happens, if you've eliminated some of the degrees, then necessarily the recurrence relation also changes. It's now no longer a second order difference operator. So you would still have a formula like this, except it would necessarily involve indexes higher than just Pn plus 1 and lower than Pn minus 1. And the eigenvalue wouldn't just be x, but some polynomial in x. So those are the exceptional orthogonal polynomials. People have been studying those since about 2008. And then what's called the Kral polynomials is a different generalization. The Kral polynomials are just like the classical orthogonal polynomials, except instead of having a second order differential operator, it's a higher order differential operator. So it involves the third or fourth or sixth or 10th derivative. And something that people have been asking me and my co-authors when we give these talks is, what about both? Are there exceptional Kral? So exceptional means this degree goes up. Kral means this degree goes up. What about both? And until just a few months ago, we had to say, we think there must be some, but we've never found any. One of the things I'll be able to announce if I get to the end of this talk is we can now say for sure that there are exceptional Kral polynomials also that have both. In case that wasn't clear enough, maybe this will help clarify it. I'm going to talk more specifically about the exceptional and classical Hermite polynomials. So the Hermite polynomials are orthogonal with respect to this inner product, the integral from minus infinity to infinity of the product of the functions times e to the minus x squared over 2. This is the so-called probabilists' version of the Hermite polynomials. It turns out that you kind of have to use that version for the results I'm going to give later, or things get much messier. It seems like it should just be a choice, but this one seems to be the natural choice for the results I'm going to present. And then the polynomials themselves have this generating function. So if you expand this out as a power series in Z, then the coefficients are polynomials, which have the required degree properties. They're orthogonal with respect to this inner product. They have a recurrence relation, which looks like this. So the difference operator is that if you take hn plus 1 plus n times hn minus 1, that's the same as x times hn for every n. And this is the differential operator that has them as eigenfunction. So those are the classical Hermite polynomials. And like I said, they're orthogonal with respect to this inner product. Those aren't the only functions that I'm interested in that are orthogonal with respect to this. So another way to think about this talk is I figured out a way to use soliton theory and the KP hierarchy to produce lots of functions that are orthogonal with respect to this inner product. And it's not just a coincidence. It seems to suggest that there's a deep connection between Hermite orthogonality and the KP hierarchy. That's one of the things I'm going to try to show you. But okay, even before I became involved, there were other functions orthogonal with respect to this inner product that people were talking about. Those were the so-called exceptional Hermite polynomials. So let me tell you about those. There's a family of exceptional Hermite polynomials for every partition that you could pick. So a partition is n numbers. I'm choosing n non-negative integers that add up to n in particular. So some of them might have to be 0. And we list them in non-increasing order. And associated to that choice, there's a family of so-called exceptional Hermite polynomials. This is how you make them. You make them as a Wronskian with respect to the variable x of a bunch of the polynomials indexed by things depending on these lambdas. So you choose these lambdas, then that tells you which n functions to put here. And then you let this last one vary. So this is n. So the nth exceptional Hermite polynomial is made this way. It's the Wronskian of the n indexed by the lambdas and this hn. And you'll notice that some of these are necessarily going to be 0. In fact, if this n here happens to coincide with any of these n numbers back there, you'll get 0. That's why there are missing degrees. So you'll have lots of different polynomials of different degrees, but n of them will be missing because of this. So I guess I have to tell you in what sense these are orthogonal polynomials. I've made polynomials for you as Wronskians of classical Hermites. All of these are classical Hermites in the Wronskian. So this goes back to the work of these authors in 2008. As I said, one of the amazing things here is the completeness. That's not something that I'm going to focus on, but these polynomials, you're still able to write every polynomial as an infinite linear combination of these, despite the missing degrees. If you take the Wronskian of just these n, so if you drop this last one off and call that function tau lambda, that's necessary for talking about the orthogonality any way you're going to do it. The way I like to do it is I like to say that if you take these polynomials, the exceptional Hermites, and divide them all by the same denominator, this tau lambda, you get rational functions that are orthogonal with respect to the Hermite inner product. So this is the same Hermite inner product I showed you before with e to the minus x squared over 2. These are now an orthogonal sequence. This is the inner product of Rm and Rn is non-zero if and only if m equals n. I guess not if and only if, because some of these are 0. So the ones that are 0, of course, have 0 inner product with everything. That's the way I like to say it. That's not the way other people like to, because people are interested in orthogonal polynomials, and these are orthogonal rational functions. So equivalently, you can say that the polynomials hn lambda themselves, these polynomials we made as Wronskians, are orthogonal with respect to this weight, e to the minus x squared over 2, the same as before, but now divided by tau lambda squared. So that's just two ways to say the same thing. If you prefer to think about it this way, where you're changing the weight and have orthogonal polynomials, that's fine. But I'm going to keep talking about it in this preferred way, that what we did is we made a bunch of rational functions that are orthogonal with respect to the Hermite inner product. And any polynomial can be written as a combination of them. So in a way, they're kind of as good as the classical Hermites, aren't they? Oh, wait, no, there's one thing I forgot to tell you. Also, again, in this 2008 paper by these authors, they showed that there's a second order differential operator, not the same one, but still, again, a second order differential operator, just like there was for the classical Hermites, that have these as eigenfunction. And so again, like I said, kind of just as good as the classical Hermites, but different in a way. Forgot to say something on there. So the last thing that popped up was one of the authors' names on that 2008 paper looked a lot like my name. It's got a lot of the same letters, and so people often think it was me. I had nothing to do with that paper. I didn't know about it at the time. I didn't learn about exceptional orthogonal polynomials until much later. So now I'm going to jump to something completely different. Maybe since there was a question, if somebody has questions about what I said so far, that was my introduction to the exceptional Hermites. All right, so something completely different. Claude-Moser matrices. These are just constant n by n matrices. So suppose you've got two matrices, x and z, they're n by n matrices, and their commutator, if you take the commutator and subtract the identity matrix from it, you get a rank 1 matrix. So this is the product of two vectors. It's got to have rank 1. So one way to think about this, especially if you're coming from mathematical physics, the commutator being the identity is an important thing, right? It's like position and momentum. We often think of this as the canonical commutation relation for position and momentum. But you can't do that in finite dimensions. It's pretty easy to show using the trace that there are no finite dimensional operators whose commutator is the identity. So you can think of this as being as close as you can get if you're doing n by n matrices. Because what does this say? This says the commutator of x and z is the identity plus some rank 1 matrix, which is as close to 0 as you can get. I don't have time. Oh, yeah. Before I move on to explaining where it came from, I can show you an example. So a very generic example. You can pick any diagonal matrix you want for x with distinct eigenvalues. So pick whatever numbers you want, your shoe size, your phone number, whatever. For the matrix z, you can also put anything you want on the diagonal. So a lot of freedom here. These can be any distinct numbers you want. These could be any numbers you want, not distinct. The only thing is the off-diagonal entries of z have to be 1 over the differences between those, which is why I need them to be distinct. And then if you choose that for your x and that for your z, you can use this for a and b. Again, just to give you a specific example, I picked x to be the diagonal matrix 1, 2. I could have put any distinct numbers I wanted there. Then on z, I put any numbers I want here. That can be irrational, whatever. These numbers on the off diagonal have to be 1 over this minus that there, and 1 over this minus that there. And if you do that, then the commutator minus the identity is the product of those two vectors. So that's how easy it is to make these. That's not all of them. In fact, there are more Claude-Moser matrices than these, and ones that aren't in this form are actually going to be important for the talk. But I just wanted to show you how many Claude-Moser matrices there are. There's basically like 2n dimensions of freedom, right? Because you could pick any n numbers here and any n numbers there. Where did this come from? As far as I know, the first people to study these were studying particle systems, the so-called Claude-Moser particle systems. These are like dots moving around in the plane as time passes, according to some Hamiltonian equation. I don't have time to explain that now, but that's where this came from and why they're called Claude-Moser matrices. And I'm going to show a connection to orthogonal polynomials, of course. But first, I need to introduce something called the adelic Grassmannian. I know people get scared of that name. I'll try to make it as simple as I can. And in fact, one of the reasons I'm introducing these Claude-Moser matrices is I think that's the easiest way to understand what the adelic Grassmannian is. Any questions about Claude-Moser matrices before I move to the next slide?
No question.
Okay. So what's the adelic Grassmannian? So you pick any pair of Kolodrov-Moser matrices you want, and then there's a bunch of, these are called time variables, T1, T2, T3, T4, infinitely many of them. This formula, which involves nothing but, well, this is matrix multiplication here, so this A and this B, since those are vectors and this one's transposed, that turns this into a scalar. So there's not a determinant here. This is a matrix product that turns out to be a scalar. And this is just e to the t1z, t2 plus t2z squared plus t3z cubed, and so on. This is what's called a wave function of the KP hierarchy. So this is what I grew up on. This is stuff I worked on for many years. You don't need to understand too many details about it. I guess what I want to convince you is that this comes from mathematical physics of waves. We call it a wave function. It's an eigenfunction for a differential operator in T1 that's called the Lax operator. And the coefficients of that Lax operator satisfy this nonlinear partial differential equation. It's a necessary consequence of coming from here. So this is a nonlinear PDE, and its solutions include things like this, like looks like a wave that you would see on the ocean. And in fact, it is a good model of ocean waves. You're not going to need to know that. I'm not going to come back and use it. The point is just that that's where this construction comes from studying waves and nonlinear PDEs. Remember, there were infinitely many times here. For this correspondence, you let x be t1 and y be t2. Those are the two space dimensions. And then t being t3 is the time variable for this. And the other times don't matter for this equation, but they show up in other descriptions like the nonlinear Schrodinger equation, the sine-Gordon equation. They're all hiding in this KP hierarchy. So what's the Adelic-Grassmannian? One way to think about it is that the collection of all these functions after running over all possible Kolodrov-Moser matrices is the Adelic-Grassmannian. And that definition comes from George Wilson in 1993. So if you're thinking about it as a correspondence between these Kolodrov-Moser matrices and these functions, because it's the collection of functions, which is the Adelic-Grassmannian, it's worth noting that it's not a one-to-one correspondence. If you simultaneously conjugate x and z by the same invertible matrix G, then you get another Kolodrov-Moser pair with the same wave function. So I guess the Adelic-Grassmannian is these Kolodrov-Moser matrices modulo this group action. You just quotient out by that. That's the Adelic-Grassmannian. That's not the definition that George Wilson gave in 1993. He didn't mention Kolodrov-Moser matrices at all. His original definition was more analytic and less algebraic. It involved derivatives, distributions in the sense of functionals, so linear functionals acting by differentiation and evaluation, and determinants. So the description in terms of Kolodrov-Moser matrices, Wilson also gave that, but that was a later result in 1998. I'm sticking to the Kolodrov-Moser matrices because I think it's easier for you to understand. But a lot of the work that was done here was actually done using these derivatives, distributions, and determinants. So I'll refer to that as the 3D approach, the 3D method instead of the Kolodrov-Moser approach. Also, to make this easier for you, even though for the KP hierarchy there are all these infinitely many time variables, in the rest of the talk I'm only going to need T1 and T2. So let's just call them X and Y and set all the other time variables equal to 0 so that they go away. And then this formula gets a lot easier to look at. Then it's just e to the xz plus yz squared, a simple function, multiplied by this. You can see now this is a rational function made out of the matrices x and z, depending on the variables x, y, and z. Another thing that I need to tie all of this together is bispectrality. So what's bispectrality? It seems like I've got several unrelated things. I'm going to have to tie these together for you. But this is actually going to tie together, at least partially, the orthogonal polynomials and the Adelic-Grassmannian. Bispectrality is just a property of functions and operators acting on them. So let's say L is an operator acting in the variable X. It could be discrete, continuous, whatever, any kind of linear operator in a variable X, any linear operator lambda in a variable Z, and a function that depends on both X and Z. We say it's bispectral triple if this function is an eigenfunction for both of those operators. So psi is an eigenfunction for L with an eigenvalue depending on Z, even though it's an operator in X. And the same function psi is an eigenfunction for the operator lambda acting in Z, but now the eigenvalue depends on X. That's called bispectrality. A couple of easy examples. E to the xz is an eigenfunction for differentiation in X with eigenvalue Z and differentiation in Z with eigenvalue X. So that's a bispectral triple. A more complicated one with a discrete operator, X to the n. If I think of the differential operator X dx, then X to the n is an eigenfunction with eigenvalue n. And if S is the shift operator that turns n into n plus 1, then since x to the n plus 1 is x to the n plus 1, we could think of S as being an operator in the variable n, which has eigenvalue x. So this is a bispectral triple. It was originally coined by, the term bispectrality was coined by Doister, Mott, and Grunbaum in their 1986 paper. They were actually doing something coming from information theory, but it's grown to be a much larger subject than that. There's a whole bispectrality community out there. And in particular, it's the link between the Adelic-Rosmanian and the classical orthogonal polynomials. Perhaps you can already see this first part that I'm going to show you. I tried to set you up for it. If we go back to the slide we already saw about the classical orthogonal polynomials, you'll notice that they are bispectral. As I showed you, the classical orthogonal polynomials are eigenfunctions for a difference operator in n with eigenvalue x, and a differential operator x with an eigenvalue that depends on n. So all the classical orthogonal polynomials are bispectral. The Adelic-Rosmanian also is bispectral, and that's why Wilson defined it. He was studying a question about bispectrality. So let's see how I can show you that it's bispectral. Remember, I had already mentioned that this function psi is an eigenfunction for a differential operator in X, the one whose coefficients look like ocean waves, with an eigenvalue depending on Z. Wilson gave this definition because it makes it very easy to see the action of something called the bispectral involution. If you set the y variable equal to 0 and just switch the x and z. So this used to be x, 0, z. We switched the x and z. That's the same as leaving the x and z in their original places, but switching the matrices x and z and transposing them. And you can kind of see that in this formula. If you set y equal to 0, so this is gone, then this is x minus x inverse, z minus z inverse. So if you switch the x and z and transpose them, that switches these two and switches their order, which is why it's the same as switching the variables x and z. The reason that's relevant to us here is we already said that this function is an eigenfunction for whatever variable is in this first position, which means that it's now an eigenfunction for an operator in z. So from this, you also get that all of these wave functions are eigenfunctions for operators in z. So all of these wave functions are bispectral. There's a differential operator in x and a differential operator in z that it's simultaneously an eigenfunction for. And Wilson didn't just want to show they are bispectral. He showed something much deeper. He showed that these are all of the rank 1 bispectral differential operators. It was a complete classification theorem. But as far as we're concerned here, just the fact that they are bispectral is the point. I learned about this stuff when I was a grad student. Before I even had started on my thesis, I proved a result about Clodrow-Moser particles using this result that Wilson had. And it got published in Communications in Mathematical Physics in 1995. I don't have time to tell you about it, but that was a pretty exciting thing for a grad student who hadn't even started his thesis yet. And a lot of what I did later for the next 10 years revolved around these things: bispectrality, particles, solitons, Grassmannians, etc. But I didn't do anything with classical or exceptional orthogonal polynomials before 2015. So that was the background. Now, how did I end up working on exceptional orthogonal polynomials? In 2015, I was at a conference in Sardinia, and I met those exceptional orthogonal polynomial people. They came up to me and asked for help. They already knew that the exceptional Hermite satisfied a differential equation like this. What they didn't know was what the recurrence relation was. I think everybody presumed there was some kind of recurrence relation that could be written this way, but they didn't have a formula for it or even a proof that it existed. And so they asked me to use my knowledge of bispectrality to figure this part out. And that worked really well. We ended up with a paper in the Journal of Approximation Theory in 2016 on this. And I felt like I was doing something very exotic. I felt like I was working on something so different than what I usually work on, because approximation theory is like the opposite of soliton theory. Soliton theory is all about getting everything exact. We didn't need approximations. So the fact that I had an article in the Journal of Approximation Theory made me think I was working on something so completely different than Wilson's Adelic-Rosmanian and KP hierarchy and all that stuff. But I was wrong, because we later realized that the exceptional Hermites had been hiding there in the Adelic-Rosmanian all the time. That it's kind of like I thought I was far from home, and I was actually right there at the house that I grew up in. Let me explain how that works. So what do I mean when I say the exceptional Hermites were hiding in the Adelic-Rosmanian all along? What I'm describing is the results of a 2020 paper that I wrote with Rob Milson. We didn't describe it in terms of Kolodrow-Moser matrices at all. We used that 3D description, so I'm not going to say it the way we did, but I'm going to give an equivalent result in the language of what I've been saying in this talk in terms of those Kolodrow-Moser matrices. So for every partition lambda, there's a KP wave function in Gur-Ad, which is a generating function for the lambda exceptional Hermites. A key to my ability to translate it into Kolodrow-Moser matrices was the work that Luc Peluso did under me at the College of Charleston in his master's thesis, where he kind of translated the results of this paper into the Kolodrow-Moser matrices for us. And that was published recently in Contemporary Math in 2025, if you want to see it. So, for example, one of the things Luc worked out is that if you pick this partition 3, 2, 1, 1, if that's your partition, then the Kolodrow-Moser matrices that will give you the corresponding exceptional Hermites are for Z. You look at this big hook in the Young diagram, 1, 2, 3, 4, 5, 6. So Z has a 6 by 6 nilpotent block, and then there's this 1 by 1 hook, so there's a 1 by 1 block, and that's all there is to say about Z. You can just read it off of the Young diagram. The X matrix is more complicated, but these are then a Kolodrow-Moser pair, and not only are they a Kolodrow-Moser pair, they're the ones that are going to give us the exceptional Hermites that we would have gotten from that partition. Here's the point. So if you use that Kolodrow-Moser pair in the wave function, and you multiply by Z to the n, that's to clear the denominator. So after I do that, this has no poles in Z anymore, so I can expand it as a series. And I plugged in -1/2 for the Y. I guess if I have time, that's going to be something I'll focus on. The Y -1/2, it turns out to be kind of important. But in any case, plug in -1/2 for the Y. Then if you expand this out, you get exactly either those rational functions, the so-called quasi-polynomials that are orthogonal, or you can think of it this way, that it's fractions whose numerators are the exceptional Hermite polynomials. And they're orthogonal. So from the Kolodrow-Moser matrices, from this KP wave function, we made functions that are orthogonal with respect to the Hermite inner product. And maybe this fact alone, that it's a generating function, isn't so interesting. The point is we were then able to use KP theory to figure out things that we still didn't know about the exceptional Hermites. So just give you 2 examples of questions. There were many questions we answered, but 2 things we could say about the exceptional Hermites after this was we knew how to find finitely supported distributions that would annihilate the entire family. So for each lambda, there's some finitely supported distributions that annihilate all the exceptional Hermites. We were able to describe that in terms of the KP theory, something that wasn't there before. And we also found a much quicker way to find the recurrence relations. Remember, that was why I got brought into this in the first place, was to find these operators. Turns out you can make them in a simple way out of the differential operators that we already knew these wave functions satisfy. So we knew that they were eigenfunctions for a differential operator in Z. There's just a translation you can do to turn that into the corresponding recurrence relation. But for me, it also raised some questions. So why is T2 equals minus a half? Why is Y equals minus a half so important in this construction? That seemed strange. So we've got two things that these wave functions satisfy. They're wave functions for the KP hierarchy. So they satisfy these nonlinear PDEs, but they also generate exceptional orthogonal polynomials. So are those two things related, or are they just two separate properties that these functions have? And what about all the other points in the adelic Grassmannian? Remember, for the n by n case, there's essentially a 2n dimensional space of Clodrow-Moser matrices, but there's only a finite number of partitions of n. So this result that we had was about just a finite number of points in a 2n dimensional space. What about all the rest of those points? Was there orthogonality there too? That was my question. And I thought about these things for 5 years, and finally I got a sabbatical this semester and really started making progress. In fact, I think I can now answer all of these questions. Let's see if I can do it in, what do I have, 15 minutes? So I had a crazy idea about how to do this. I don't think my co-authors were convinced that this was going to be sensible. Usually when people are talking about a bunch of functions being orthogonal, they just plug each individual function. So take R sub m and R sub n separately and plug them into the inner product and see if you get 0 or not, right? But I wanted to do it with the generating function instead. So this is a generating function for these orthogonal rational functions. If you take two copies of that generating function, one with a variable z that you're expanding in, and the other one, just call it something else, like w, then if you plug those into the inner product, orthogonality corresponds to saying that the result you get is dependent just on the product of those two variables, w and z, not f of w comma z. It doesn't depend on the two variables. It depends on their product. I think I can explain why. If you expand these out, so if you expand out both of the generating functions this way and then distribute the inner product, you'll see that the coefficient on this right side here, the coefficient of w to the n, z to the n, will be just the inner product of Rm, Rn. And what does it mean if they're orthogonal? If there's orthogonality, then when m and n are different, this coefficient is 0. So the only times you see w to the m, z to the n with a non-zero coefficient is when m equals n, which is why this turns out to just be a function of the product, wz. The reason I was interested in that is I knew that the KP wave functions also have an integral formula with the two wave functions in it. The KP hierarchy can also be written this way. So equivalent to all the nonlinear PDEs is this integral formula that two copies, two different wave functions, when integrated around a big loop, give you 0. So it's a 0 residue formula. And I was focused on the fact that these look kind of similar and thinking maybe this is the connection between KP, because this is somehow equivalent to all the nonlinear PDEs. Somehow this is the connection between KP and orthogonality, is that these two things are in some way the same. But I have to admit, I can see why my co-authors were skeptical. There are a lot of differences between these. This is an integral in x. This is an integral in z. That seems worrisome, but don't forget, these wave functions I'm talking about are bispectral. So you can swap x and z. Okay, so not a big deal. This one has an e to the minus x squared over 2 in it. This one doesn't. That seems like a problem. This one's an integral from minus infinity to infinity. This one's around a loop. There are differences, but I was worried. I still was confident somehow this was going to work out. So the first thing I needed to do was figure out what the two wave functions were in that integral formula. I didn't emphasize it when I was there, but the integral formula for KP involved an x star z star. So some other Colodro-Moser pair, so that the integral of this wave function and that wave function has zero residue. And it took me a while to figure this out, but it's just a simple map. So you just transpose the x and z and change the sign. It's not the bispectral involution where you transpose x and z and swap them. You leave them in the same places, but you put a minus on z. That's also a Colodro-Moser pair. And then from KP theorem, I didn't even really have to prove it. Everybody already knows this. That means that this integral is going to be zero, the integral around a loop of these. So you can put any Colodro-Moser matrices you want there. And I was trying to figure out how to turn this into orthogonality. So what did I wanted to turn that z into an x. So what I did is I switched the variables around and then applied the bispectral involution, where you switch x and z. And I get a formula that's true. This formula is true, but it's not what I want. I mean, there are two problems with it. One is I want a -1/2 here instead of a 0. The other is that I needed an e to the minus x squared over 2. I need the weight function in there. So that's where I was like last summer. I'm not sure I'd gotten much further than this, even at the conference in Miami where I met a lot of you. But then a miracle occurred. If instead of plugging in y equals 0, which is what one normally does when applying the bispectral involution, if instead you use y equals -1/2 and you apply it to this, you get this formula. You get -1/2 in there, and this e to the minus x squared over 2 appears magically. I think I don't have time to show you that. I would if I had more time. It's actually pretty simple. It's not a complicated theorem, but basically, the bispectral involution is as simple as switching x and z as long as all of the times are 0. But if t2 is not 0, if it's -1/2, this magically appears, which was an indication to me that I was on the right track, because I thought I had two problems, that this was in z instead of x, and that this function wasn't there. But it turns out solving one of the problems solved the other. That this was an indication to me that I was going to be able to connect these two formulas. So I'm going to skip to 16. If there's more time at the end and anybody wants to see this, I can come back and show you how this e to the minus x squared over 2 appears there. Now I can state the main result. So for any Colodro-Moser pair, you take this normalized version of the wave function. So this is the wave function that George Wilson already talked about, and I'm just normalizing it, multiplying by the characteristic polynomial of z, because then this becomes a holomorphic function in z. Now I can expand it as a power series. That's really the only reason that's there. It's not anything deep. And then I also do the same thing for, this is the bispectral involution. You swap x and z and transpose them. So I look at this wave function and the wave function of its bispectral dual, and I evaluate them at y equals -1/2, expand them out, and I get two series. So from this one, I get a series I'll call F, and from this one, I get a series I call G. And the point is that F and G are mostly orthogonal with respect to the Hermite inner product. To give more details, I also need this doubly normalized wave function. So this was normalized. I cleared the denominator of poles in z. This is just doubly normalized. I clear the denominator of poles in z and x. And the other weird thing about this, which is kind of, to me, part of the mystery, is these are evaluated at y equals -1/2. This one is evaluated at y equals 0. But if you expand it out at y equals 0, you get some polynomial times e to the xz. And what matters to me is which powers of x and z appear in the polynomial. So if you just define B to be the set of I minus j for all of the i's and j's that appear with non-zero coefficients, then it's a finite set. It's just got integers between minus n, and big N, where n is the size of the matrices. So there's a finite set of numbers called B. And the point is that tells us which elements of the sequence F and the sequence G must be orthogonal. So the most general statement is that Fm and Gn always are orthogonal whenever m minus n is not in this set. So in the set B, which is just a finite set. So most choices of m and n, you'll get orthogonal functions. More specifically, if we're talking about, oh, and so I forgot, I call that almost bi-orthogonality. So the sequences F and G are almost bi-orthogonal. If the point happens to be a fixed point of the bispectral involution, so if switching x and z doesn't change anything when y is 0, then the two sequences are actually the same. The sequence F and the sequence G, they're just two different names for the same sequence. So then we can say that the function G is almost orthogonal to itself. And if the wave function is not only symmetric, but actually depends just on the product xz. So if as a function of x and z, it's really just a function of x times z, then the almost goes away, and there's actual orthogonality. So we actually get that the sequence is an orthogonal sequence, and in fact, then it's the exceptional Hermites that we already saw, corresponding to some lambda. So summary is, each function in one of these sequences is orthogonal to almost all of the others with respect to the Hermite inner product. And we can recover the exceptional Hermites as a special case where the wave function satisfies this. The proof starts with the KP hierarchy written in that integral form. Then I'm able to compute the inner product of the generating functions with each other. And it also turns out to be that doubly normalized wave function. So this is the inner product of those two. That's the amazing part. I do that by using the rank 1 condition a bunch of times and the 0 residue property a bunch of times. It says that we could look at a key lemma on the next slide if there was enough time, but it doesn't look like there is enough time. So here's an example. These are Kolodro-Moser matrices. This one has a T in it just because I wanted to show you one parameter family of them. But truth is, you can plug in any constant for T. These are Kolodro-Moser matrices. And what do we get from these Kolodro-Moser matrices? If you expand out the generating functions, which are these normalized KP wave functions, the one for that Kolodro-Moser pair and its bispectral dual, evaluated at y equals -1/2. These are the generating functions. You expand them out, you get a bunch of rational functions, all with the same denominator. X cubed minus 3t is the denominator on all of them. And so they look like these kind of things. These are some F's. These are some G's. There are infinitely many of them because the degree keeps going up in the numerator. And they're mostly orthogonal to each other. F0 and G1 are orthogonal, F2 and G1 are orthogonal, F2 and G3 are orthogonal with respect to the Hermite inner product. But they're not quite orthogonal. F0 and G3 have a non-zero inner product, at least when T is non-zero. And I can figure that out in advance by looking at this wave function at 0. So if instead of plugging in -1/2, if I plug in 0 for y, this polynomial in the numerator tells me when they're going to be orthogonal. The powers of x minus the power of z, 1 minus 1, 2 minus 2, 3 minus 3, those are all 0. This one, there's no x. So x to the 0, 0 minus 3 is -3. So that means the set B would be -3 and 0. That's why these are not orthogonal when the indices differ by 3. But notice that there's a t here. That's why I put the t in. If t is 0, something very different happens. If t is 0, this term goes away and all the differences between the exponents are 0, which means then they would be orthogonal. So if I plug in t equals 0, okay, here's another way to see it before I get to that. So the set B is -3, 0. That means they're not orthogonal sequences. They're not orthogonal to each other. Their inner product has this delta function at mn, but also a delta function at mn minus 3. It's easy to see if you look at the matrix of inner products. So the this inner product for mn is in the mth row and nth column here, and you see there's non-zero numbers on the diagonal and non-zero numbers on the super diagonal. But if t equals 0, then this term goes away, these are all 0, then you get actual orthogonality, and those are the exceptional Hermites, which people have been studying since 2008, but I kind of derived them without even knowing that from the KP hierarchy. So what I do and don't like about this, I think I need 2 more minutes. I'll be done pretty soon. This is the result. What do I like about it? What do I not like about it? I like that I was actually able to do it. I derived the orthogonality of the exceptional Hermites starting from the dynamical equations of the KP hierarchy, using the techniques I thought I could use, even though a lot of people thought it wasn't going to work. It did. So I like that. And I like that it seems to show that there's some deep connection between the KP hierarchy and the orthogonality of exceptional Hermites, because I mean, what turned out to be important? The bispectral involution, which people have been studying since 1993, was important here, even though it wasn't developed for exceptional Hermites. It was important here. And the KP times were important because we had to plug in -0.5 for y sometimes and 0 for y other times. So I think that shows that there's a deep connection between the KP hierarchy and the exceptional Hermites. What I don't like about it is I was hoping that some of those other points in the adelic Grassmannian would give me other orthogonal sequences. For example, secretly I was hoping I was going to find exceptional crawls. There were all these many points. I thought maybe one of them or all of them or something would give me exceptional crawls, but all the other points in Gerad, other than the ones that are exceptional Hermites, give you either almost orthogonal or almost bi-orthogonal sequences, never just orthogonal. So that would be a downer of a place to end this talk. That would be a sad place to end the talk if I was going to stop there, because I didn't get what I want. But if you give me another minute, I'll quickly announce we also, in a related project, found lots of exceptional crawls. We haven't really explained the connection, but there's a connection between what I talked about here and a procedure that lets us find lots of exceptional crawls. We announced it in a preprint where we showed some of them, but we haven't really said the whole thing yet because, to be honest, we're still a little bit confused about how it all works. But something interesting is going on, and it does let us get exceptional crawls. Most of what I said in this talk is in this preprint. You can also see our first announcement about the exceptional crawls in that preprint. There's a lot of stuff I'm still working on, like I'll make an announcement here for the first time. I think I now have enough results to say with confidence that it's not just the Hermites. We're also going to be able to get other classical polynomials and their exceptional corresponding sequences from a construction very much like the one I already showed you. And I'll stop there. I'll thank Luis for inviting me, and thank you all for listening. And let me know if you have any questions. Thank you.